Hello, Pre-Calculus Level 1 students. We're going to try something a little different today, and you guys are going to learn 15.5, which is the binomial theorem in using Pascal's triangle, online. It's a pretty straightforward section, and it's really important for when we get to probability, because in Chapter 16 we're going to do binomial probability, and you'll use a lot of the information that you learn from this section in that section. So Pascal's triangle. You've probably heard of Pascal's triangle before, but maybe you don't remember exactly what it is. Some of you may have some recollection, some of you may not. So here's what Pascal's triangles look like. It starts with the number 1, and then the next row increases by a number. So the next row is 1, 1. The third row would be 1, 2, 1, and the fourth row would be 1, 3, 3, 1. Now you may be wondering where I got these numbers from. So here's how Pascal's triangles work. You look at the two numbers above in order to get the next number. So for example, to get the 2, I added the 1 and the 1, and that's how I got 2. In the third row, to get 3, I added the 1 and the 2. And the same thing with the other 3. So you're adding the two numbers before it, or above it, I apologize. And the outside number is always 1. So if I wanted to continue Pascal's triangle, I know that the outside numbers are always 1. And then to get the next numbers, I add the two numbers above it. So it would be 4, 6, and 4. And then just to do one more line, we could have 1, 5, 10, 10, 5, and 1. You may start to notice that there's a lot of interesting patterns in Pascal's triangle, other than the whole ones down the side. If you're to look closely at either this diagonal, or we have the same diagonal going in the other direction, you notice that the numbers increase by 1. If we were to look at the next diagonal, here, you'll notice that the number first increases by 2, then it increases by 3, then it increases by 4, and that pattern's going to continue. So there's a lot of actually interesting patterns you could look for in Pascal's triangle. The last one that you might see right away that's going to be really interesting to us when we start looking at the binomial theorem is that Pascal's triangle is symmetrical about the middle. So here are the middle numbers, if there is a middle number, and you'll notice that on both sides the numbers are the same. So example, in the last row, we have 1, 5, 10, and using our symmetry from geometry, we have 10, 5, 1. So that kind of helps you when you're trying to use Pascal's triangle. But it would be a pain to use Pascal's triangle to write out every single row. So we have a shortcut that we're going to use in this section. So we're going to help use Pascal's triangle to expand binomials. Just in case you don't remember, a binomial is some polynomial with just two terms. So if you look at all of our parentheses, we have a plus b. There's your polynomial with just two terms in it. Now we're going to expand each one of them. First one's pretty easy. A plus b to the first power would just be 1a plus 1b. No big deal. A plus b squared. Well, we know that we would have to FOIL that out. So we'd have to do a plus b times a plus b. Not that bad. We hopefully know that we get a squared plus 2ab plus a. We could keep going. If we were going to do a plus b to the third power, now you're going to have to FOIL, and then you're going to have to multiply by a plus 3 again. A plus b again. That can be a pain. So let me just show you what that would be. And you could take the time if you want to on your own if you don't trust me, which I totally understand. But if you were to expand this, you end up with 1a cubed plus 3a squared b plus 3ab squared plus 1b cubed. So that's not too bad. Now if I wanted to do a plus b to the fourth, I'd essentially have to take what I just got and multiply that through by a plus b. So another whole term of a plus b. So what you would get if you expand that is 1a to the fourth plus 4a to the third b plus 6a squared b squared plus 4ab cubed plus 1b to the fourth. Now, if you took notes on the last slide on Pascal's triangle, you might start to notice something really interesting, that here is the second row of Pascal's triangle, 1, 1. And if we were to look at the next one, the third row of Pascal's triangle is 1, 2, 1. Fourth row, 1, 3, 3, 1. Fourth row, 1, 4, 6, 4, 1. So these coefficients that we're getting by expanding our binomials are actually coming from Pascal's triangle. The other thing that's really interesting and really important to know about this is if you look at the sum of the exponents, a squared is the only exponent there. It's equal to the original exponent. A to the first, b to the first. We have an exponent of 1 and 1, adds up to 2. And then, this should have been b to the second over here. Again, adds up to 2. And if we were to go through all of them, you would see that. So here we have a to the fourth, 3 plus 1 is 4, 2 plus 2 is 4, 1 plus 3 is 4, and we have a 4 again. That's also going to be really important in helping us expand these in a shortened way. So again, all of the numbers in Pascal's triangles are called the binomial coefficients, because when we expand our binomials, those numbers become the coefficients in what we just expanded. So just to help you out and get you ready for the next slide, if I had x plus 4 to the fifth, what we're really doing is x plus 4 5 times. So it looks something like this. There's 4. So there are your x plus 4 to the fifth. So we have one x plus 4 to multiply by a second one, a third, a fourth, and a fifth. So we have 5 of these that we need to multiply together. Now, in all reality, it doesn't matter which two you multiply together first. We can multiply these two together first. That would be totally fine and probably a route that most people would take. Or we could choose to multiply the last two together first and then distribute the third one, or lots of different combinations that we can use. The important part that you realize about this is that there are so many combinations that it doesn't matter which two you choose to multiply first. It just matters that we're choosing 2 of them. So that's going to be important when we're trying to figure out the binomial theorem, or a shortcut to expand this. So I'm going to give you the formal definition of this and then try to explain it using an example. So I like to think about this in terms of b. So when we're first starting out, when we're trying to figure out our first term, you'll remember that it had all a's in it. It didn't have any b values. So when we have something raised to the n power, here's how I like to think about it. We have n combinations of b, but we don't want any b's in the first term. So I'm going to put a 0 there. So we have n b's, but I'm choosing none. And then I'm going to have my a to the nth power, because if you notice, the first term is always raised to the same power of the original power in the problem. And then b to the 0, because we didn't want any of those. For my second term, again, I have n b's to choose from, but this time I'm choosing 1. So it could be a b from the first parenthesis, the last parenthesis, the third parenthesis. It doesn't matter. All I know is that there's n b's, and I'm going to choose 1 this time, which means I have 1 less a. So a to the n minus 1, 1 less, and then b to the first power. And we're going to keep working through each term this way. So the next term would be that I have n b's to choose from, and this time I'm choosing 2. And then we would have, again, 1 less a than before, so n minus 2 this time, and then b to the second. And we would continue on in this fashion, we would continue on in this fashion until we got to the last term, which would be, we have n p values. This time we're choosing all of them, which would be n. We want no a's, and we want all b's. So we would continue in this fashion. Again, one way to tell if you're doing this correctly or not is that your exponents should always add up to the original number. So again, n plus 0 is n. n minus 1 plus 1 is n minus 2 plus 2 is n. And again, this exponent, or this number, should always be the same as the exponent with your b. So here's our first example. We want to expand 2x minus 1 raised to the 4th power using the binomial theorem. So we're not looking at Pascal's triangle. So in order to do this, we're going to start with, obviously, our first term. And in term 1, we have no b's. So if I want no b's, and there's going to be here, our b value is going to be negative 1, and our a value is equal to 2x. We're going to go through this plugging in the 2x for the a's and negative 1 for the b. So we have how many b's? Well, we look at our original exponent, 4. So we have 4 b's, but we're choosing 0 of them. And then we have our a, which is 2x, and I want all of those, so it's raised to the 4th power. And we have b to the 0 power. Now technically you don't have to include that because it is equal to 1, but just because it's our first time through, I'm going to include it in here. Then I want my second term. For my second term, we want 1b. This is the second. We want 1b. So we're going to have 4 b's. This time we're choosing one of the 4. And then we're going to have our a value raised to the 3rd power, and we want 1b. Again, the a's decrease every time. The b's are going to increase every time. For our third term, we want 2 b's. So here we have 4. We're going to choose 2. And then we have our a squared times our b squared. Apologize about the writing. It's getting a little messy. And then for our fourth term, we want 3 b's. So I have 4 b's. I'm choosing 3. I want my a to the 1st power and b to the 3rd power. And then for my 5th term, I want 4 b's, which would be all of them. And that's how I know to stop. It's because I have 4 and I'm choosing 4. So I know this has to be my last term. So I want no a's for this one and 4 b's. Now if I were to do out all this math, which I don't have that much room, so I'm just going to give you the answer, and hopefully you could go through, use your calculator, and find the answer for this, and you can compare. You should have 16 x to the 4th minus 32 x to the 3rd plus 24 x squared minus 12x plus 1. You may be wondering why this first one has a coefficient of 16 and not 1, and that's because my a value had a constant with it. If it didn't have a constant with it, it would just end up being x to the 4th. But we have to take our a value and raise that to the 4th. So that is why we have a coefficient with our first term.